Welcome to the deep dive. We're here to cut through all that information noise and really get straight to what matters.
Yeah, especially with these complex tech topics.
Exactly. It's easy to get swamped. So our goal today is to give you that shortcut, that deep understanding without the overwhelm.
And today, we are diving into something pretty exciting in natural language processing, NLP.
Hmm?
We're going to unpack a really interesting development.
Right.
This new family of multilingual models they're calling EuroBERT.
EuroBERT.
Yeah.
Okay.
And our mission, really, is to pull out the key insights, maybe some surprising facts, too, from their research paper, all for you.
Sounds great because, it feels like for a while now, these traditional encoder models, the
Yeah.
ones for like search or classifying text,
Right.
they've sort of been overshadowed, haven't they?
Definitely. All the buzz has been around the generative ones, the decoder-only models, the chatbots everyone's using.
Right. And what's really interesting, and maybe you can shed some light here, is why those decoder advancements didn't really make their way back to the encoders sooner. It feels like a gap.
It's a good question. I think research often goes down specific paths. Decoder innovation was just so fast.
Right.
But this EuroBERT work, it shows a deliberate effort. A team from, all across Europe and beyond basically decided to bridge that gap.
So taking the new tricks and applying them back.
Exactly. Taking the best of modern decoder design and sort of refreshing the recipe for encoders. Our source today is their paper detailing all this. We've boiled it down.
Okay, let's unpack it then. What is EuroBERT fundamentally, and why should we care?
Okay, so EuroBERT is a family of what they call general-purpose multilingual encoder models.
Right.
Basically, an encoder's job is to read text, understand the meaning by looking at words in context before and after.
The whole picture.
The whole picture, yeah. And then it turns that understanding into a numerical format, a dense vector, they call it, like a summary in numbers.
And these vectors, these number summaries, I assume they're pretty useful.
Oh, absolutely. Super versatile. They're the foundation for so much. You use them for retrieval finding stuff.
Like search?
Exactly. Or classification sorting text, figuring out sentiment,
Oh.
or even regression, like predicting a score for translation quality, maybe.
And the key thing with EuroBERT is that it explicitly uses those decoder innovations we talked about.
That's right. It takes those cutting-edge ideas, the architecture tweaks, the data improvements from the generative revolution, and applies them back to this, older but still vital encoder tech.
So it's not just a minor update, it's a real refresh.
It really is. And a big advantage it brings is handling much longer text natively. We're talking up to 8,192 tokens.
Wow, that's quite a bit compared to older models.
Yeah, it's a significant jump. Many older ones struggled with that kind of length efficiently. It means it can grasp the context of a really long document.
So connecting this back to you listening, what's the practical payoff here? What does this unlock?
Well, it means more powerful, more nuanced tools for handling information in lots of languages.
Okay.
Think about search results maybe getting more relevant, more context-aware, or sentiment analysis that gets the subtleties across different cultures.
Right.
For anyone dealing with loads of text in different languages, this could mean much more capable, much more accurate AI applications. It's a real step up.
Okay, let's peek behind the curtain then. The recipe for EuroBERT. You mentioned architectural changes borrowed from decoders. Can you walk us through some specifics?
Sure. They brought in several pretty sophisticated ideas, like removing biases entirely from the model.
Okay, like Llama 2 did.
Exactly.
Yeah.
That helps with stability and performance. They also use things like grouped query attention,
It helps with...
handling those long sequences more efficiently. Then there's technical stuff like switch-gated linear units, RMS norm, root mean square layer normalization.
Right, components for better learning.
Yeah, they help the model learn better and keep things stable. And finally, rotary position embeddings.
For understanding word order.
Precisely. Gives it a better grasp of how words relate in sequence.
Mm.
These are all, individually, maybe subtle, but together they make a big difference in how the model works and scales.
And the architecture is one thing, but the data, you said 5 trillion tokens. That's just huge.
It's staggering, yeah. 4.8 trillion for the main pre-training, and then another 200 billion for what they call an annealing phase.
Annealing phase. Is that like a refinement step?
Kind of, yeah. Think of it like fine-tuning, but maybe a bit broader. It's a second training stage where they adjust things like the data mix or other parameters to optimize for the tasks it'll actually be used for.
And this data covered 15 languages?
Yep. English, French, German, Spanish, Chinese, Italian, Russian, Polish, Portuguese, Japanese, Vietnamese, Dutch, Arabic, Turkish, and Hindi.
Quite the mix. Was there a logic to the selection?
Yeah, they aimed for a balance. European languages, sure, but also major global ones. Different alphabets, different language families, trying to get broad coverage.
And the data sources themselves had some surprises, right? Beyond the usual web texts like FineWeb or Cultura X.
Definitely. They included EuroLEM parallel data that helps with translation-like tasks, understanding across languages.
Makes sense.
But the real curveball was including the Stack v2, that's code, 38 programming languages.
Code for a text model.
Yeah, and ProofPile 2, which is mathematics.
Math as well. Why add code and math to a multilingual text encoder?
Well, the thinking, or the hypothesis maybe, came from the decoder world again. They found adding code sometimes helped even general language abilities. So the idea was maybe these structured data sets could help the encoder learn complex patterns too.
Interesting gamble. And the training itself, it used masked language modeling, MLM?
Correct. MLM is where you hide some words in a sentence.
Mask them out.
Right. And the model has to predict what's missing based on everything around it. It's a great way to force it to learn language structure, context, grammar.
And they did this in 2 phases.
Yeah. Pre-training started with a really high masking ratio of 50%.
Half the words hidden. Wow.
Yeah, sounds like a lot, but research suggested bigger models actually benefit from more aggressive masking early on.
Okay. And then the annealing phase.
Then they dropped the masking way down to 10%.
To make it more precise.
Exactly, to hone its performance on actual tasks. And they also tweaked the data mix in this phase, focusing more on higher quality text, using a classifier they developed.
Got it. And managing that long context length, 8,192 tokens, how did they handle that practically in training? Pre-training was shorter, right?
Yeah, pre-training used 2,048 tokens. For the annealing phase, where they went up to 8,192, they used a clever trick, randomly cropping documents.
Instead of feeding it perfectly sized chunks.
Right, and the surprising thing, this random cropping actually worked better than training on fixed 8K chunks for long context performance.
Huh. So a bit of randomness helped it generalize.
Seems like it. Exposing it to variable lengths, maybe making it less reliant on perfectly formatted input.
And pulling this all off required some serious hardware, I imagine.
Oh yeah, trained on the Adastra supercomputer, hundreds of high-end GPUs, MI250X, MI300A, totaling about 200,000 GPU hours.
That's a lot of compute. Really underscores the scale of these projects.
Absolutely. Building these cutting-edge models takes massive resources.
So the models built, trained on this huge data set with all these techniques. How did it actually perform? What tests did they run?
They really put it through its paces, a wide range of typical encoder tasks, multilingual retrieval, naturally.
Finding information.
Yep. Then various kinds of classification, sentence level, token level, but also specialized classification for code and math problems.
Ah, testing that code math data inclusion.
Exactly. And also sequence regression, things like judging translation quality or how good a summary is. Pretty comprehensive.
And who were they comparing it against? The established players?
Yeah, strong baselines like XLM Roberta, MGTE MLM, MDBERTA v3. And for code and math, they brought in English-only specialists like ModernBERT. So, a tough field.
And how did EuroBERT fare overall? Did it hold its own?
It did more than hold its own, showed really strong performance across the board. The biggest one, EuroBERT 2.1b, actually came out top on 10 out of the 18 tasks.
10 out of 18? That's impressive.
Very. And even when it wasn't first, it was competing closely with models that are much, much larger.
That efficiency point seems key. I think you mentioned the 610M model performed like something 5 times bigger.
Yeah, that was a standout result. The EuroBERT 610M, so 610 million parameters, performed comparably to XLM Roberta 3.5b, which is 3.5 billion parameters.
Wow. So you get similar power for much less cost, basically.
Exactly. Less compute, less memory. That's huge for actually deploying these things. And even the smallest one, the 210M, punched above its weight, especially in European languages, shows the whole family is efficient.
Okay, looking at specific areas, retrieval, finding information.
Consistently strong. Ranked high across different retrieval tasks. Even the smaller EuroBERTs often beat competitors there. So excellent in finding relevant info.
And what about that code and math gamble? Did including that data pay off?
It really seemed to. The EuroBERT models excelled in code and math tasks, consistently outperformed the others. Even the little 210M model did remarkably well, often beating all the baselines.
So that diverse data really built some robust pattern recognition.
Looks like it. It suggests that including structured data like code and math genuinely helped, even beyond just those domains.
And the long context capability, 8,192 tokens. Did that hold up under pressure?
It did. That was crucial. EuroBERT maintained its performance levels even when processing those really long sequences.
Whereas others might struggle.
Exactly. They specifically noted that a competitor like XLM Roberta showed notable degradation at those longer lengths. So EuroBERT's ability to handle long context is a real practical advantage.
Okay, but it can't be perfect everywhere. Were there areas where it was more average or where they saw trade-offs?
Yeah, for sure. In sequence classification tasks like sorting sentences, its performance was good, generally on par with the competition.
But not necessarily leading.
Right. And the researchers themselves pointed out that some design choices seemed to create a trade-off. It was so good at retrieval, that might have come at a slight cost to its classification ability.
Interesting. A balancing act.
Always. And for token classification, like finding names or places in text, named entity recognition.
In ER, yeah.
There, it lagged a bit behind some rivals. They had a hypothesis, though.
Oh, yeah.
They thought it might be down to how its tokenizer works,
Yeah.
how it splits words into pieces, the fertility they call it, or maybe just the size of its vocabulary compared to others.
Technical details that can have downstream effects.
Definitely.
Let's switch gears a bit to the really surprising stuff. The insights from the training process itself. These often challenge our assumptions, like language balancing. We usually think more balance is always better.
Right. But they found something nuanced. Balancing the languages during that annealing phase did help overall, up to a point.
Really up to a point.
Yeah. Making the language mix too perfectly uniform actually made performance worse.
Huh. So perfect balance isn't the goal.
Apparently not always. It suggests there's maybe an optimal level of diversity, and making it too flat can hurt. The art of data mixing, perhaps.
Fascinating. And that code and math data inclusion, we said it helped, but was it universally positive?
No. Another trade-off there. It significantly boosted multilingual retrieval.
Good.
But it actually degraded multilingual classification performance.
Oh, really? So helping one task hurt another?
Exactly. It just highlights how complex these multitask models are. Optimizing for everything simultaneously is really hard. What helps search might hinder categorization.
But some things were clear wins, right?
Oh, yeah. Parallel data, having texts translated across languages consistently helped everything. More parallel data boosted both classification and retrieval.
Oh.
That was unambiguous.
Okay, good to know. Now, this next one feels really important, maybe even counterintuitive for many in AI. Data quality. The assumption is usually use only the best quality data you can find.
Right. That's the standard wisdom, especially for training those big assistant models. Filter aggressively, keep only the pristine stuff.
But that's not what worked best for EuroBERT.
No. And this is a really key finding for you listening. When they tried using only the highest quality data during annealing based on this educational value, metric performance actually went down.
Went down, using only the best data.
Yeah. The best results came from mixing what they called quality levels 3 and 4, not just the absolute top tier.
Why would that be? Any ideas?
They suggest a domain mismatch. What we think is high quality for a chatbot might not be the best diet for a general-purpose encoder that needs to understand, well, everything, messy web text, technical documents, the lot.
So a broader range of data, even if not perfectly high quality, might be better for robustness.
It seems so for this kind of model. It definitely challenges the idea that more filtering is always better. Depends on the model's job.
That's a huge takeaway. And you also mentioned variable lengths helping during annealing.
Yes, varying the sentence lengths fed to the model significantly boosted performance, particularly for classification.
And the random cropping we talked about earlier?
That ties in. That random cropping technique proved really effective, even better than carefully feeding it fixed-length chunks for long context training. Again, maybe that variety helps.
And finally, the masking ratio. High for pre-training, lowered for annealing. That also had trade-offs.
It did. Lowering it to 10% for annealing definitely helped classification scores, but it slightly reduced retrieval quality. So again, a tuning knob with effects in different directions. No single setting is perfect for all tasks.
Okay, so wrapping this all up, this whole deep dive into EuroBERT, what's the big picture message for you, our listener?
I think it really shows that AI innovation isn't just about brand new architectures or just making models bigger.
Right.
It's also, crucially, about revisiting existing ideas, like encoders, but with fresh eyes, applying lessons learned elsewhere. like from decoders.
And it really underscores those complex trade-offs, doesn't it? In the architecture, the data, the training.
Absolutely. Things that seem obvious, like use only the best data or keep the masking rate consistent, well, they aren't always right. The reality is much more nuanced
Counterintuitive results pop up.
all the time.
Mm.
And for people actually working in NLP, the fact that they released the EuroBERT models, the checkpoints, even the training code, that's huge.
A powerful new tool and a base for more research.
Exactly. A strong, efficient foundation for building better multilingual understanding systems.
So maybe the final thought here. This journey into EuroBERT suggests the secret sauce in AI isn't always some single giant leap. Often it's this careful, almost artistic balancing act, juggling architecture, data, training methods, trying to combine things that might even seem conflicting.
Yeah, it makes you wonder, right? How much progress is just raw scale, more data, more compute, versus how much is this subtle art of combination, finding clever ways to blend different insights?
What other counterintuitive findings are just sitting there waiting in the data or the model designs if we only look differently? That feels like the big question moving forward.